welcome to this revision video. Today we're going to be looking at making fertilisers in the lab, which is a triple chemistry only practical. So for this practical, what I'm going to be doing is reacting together dilute ammonia and dilute sulfuric acid to produce ammonium sulfate, which is a fertiliser. So I'm going to be doing the reaction as a titration because it is a neutralisation reaction. So I've got my burette and my conical flask ready with my chemicals already, and I'll show you a little video in a second of how I set those up. So I've got my sulfuric acid in the burette and I've got my ammonia in the conical flask, and what I'm going to do is I'm going to do a titration. I'm going to do it 3 times to be able to calculate a mean, and then after I have completed the reaction I'm going to be crystallising the ammonium sulfate to give us our fertiliser crystals.
So here's a time lapse of how I fill my burette with the sulfuric acid, which you can see here. So I've got a funnel and I'm going to place my burette on the floor because it's not safe for me to be pouring it into the burette above the level of my head. So I'm just filling it up, filling it all the way to the top. Need a little bit more acid, and then I'm just draining out a small amount to make sure it starts at 0. So here's another time lapse to show how I fill my glass pipette with the ammonia solution. So I've got my solution in a beaker and a conical flask. I've got my glass pipette and my rubber pipette filler. Now you've got to make sure you hold the end of the glass pipette to add the pipette filler and then squeeze out all of the air. Then you can push the button to slowly draw up your ammonia solution, and it will draw up exactly 25 centimetres cubed. It's much more accurate than using a measuring cylinder, and then I just allow it to drain out into the conical flask. And you can touch the surface of the solution at the end to draw out the last few drips before placing it safely on the desk so it can't roll off, and pouring the excess ammonia back into the bottle and sealing it.
So now I'm set up and ready to begin the titration. Now this titration is a little bit different from those that you may have done previously, for example between sodium hydroxide and hydrochloric acid, where you would add an indicator into your conical flask. Now if I added an indicator into this conical flask to tell me when I reach my end point, that's going to interfere with my ammonium sulfate that's being produced, because that is what I actually want at the end. I want to crystallise it and I don't want any indicator to be in there. So what I'm going to use instead is some litmus paper, and I'm going to be dabbing in a glass rod as I go through and putting that onto some litmus paper to show me when I have reached my end point. So due to the size of the burette, it would be very difficult for you to, closely see what I'm doing. So I'm going to focus on what's going on just above the conical flask for this. Now, we have to do this titration in a slightly different way as well than to account for the lack of indicator. I can't just let my sulfuric acid run into the ammonia because I'm not going to know when I'm reaching that end point, unlike when we've got the indicator in there and it starts to change colour. So what I'm going to have to do is I'm going to have to be very careful. I'm going to have to add in my solution 1 centimetre cubed at a time and keep testing it. So that's what I'm going to do, and I'm going to go through the process and we're going to look until the litmus paper starts to turn pink when I dab on my glass rod that's been dipped into the solution, because blue litmus paper, it's blue in alkaline, pink in acidic conditions, so that'll tell me that I'm reaching neutralisation, or I've reached neutralisation when it just turns pink. So I'm looking to get my endpoint, so I'm going to be very carefully adding in my 1 centimetre cubed at a time. Swirling it, and then I will dab it onto the paper, and we can see that quite clearly blue. So I'm going to add in another centimetre cube. I'm just going to tighten this up a little bit. Okay. It only needs to be roughly 1 centimetre cubed at a time, but it's just so that we don't add too much at once. Still blue. So I'm just going to keep going now and keep testing it. I'm going to speed this video up a little bit until we start to reach that end point. So what I'm doing now is I'm going to start adding it a little more slowly as I seem to be nearing the end point. So that's gone very pink now. Okay, so I think we've gone past our end point slightly. So I think it was probably, you know, a few tenths of a centimetre cubed less than what I've just added. But you can see now that my litmus paper has definitely turned pink. So I'm going to add in again. Is it still pink? Yeah, it's still pink. So sometimes when it wasn't mixed and I was getting a little bit of the sulfuric acid, it wasn't coming out as what I would have expected. So what I'm going to do now is I'm going to record the volume that the volume of sulfuric acid that has been added at this point. I'm going to record that. I'm going to use this as a little bit of a rough titration, and I'm going to try and do this a couple more times to get some concordant results to be able to calculate the mean. So, the titrations must be repeated until you get 2 concordant results. That means that you've got 2 results that are within 0.1 centimetres cubed of each other. Now, luckily for me, I did 2 titrations and they were both concordant. So I measured a volume of 10.25 centimetres cubed of sulfuric acid that has been added to my ammonia. Now, we could use this if we didn't know the concentration of either the ammonia or the sulfuric acid. We could, of course, use the titration to calculate that concentration. However, that's not something that we need to do for this practical today. So the final thing that I'm going to do is I am going to start to crystallise my ammonium sulfate. So the final step in this process is to crystallise our ammonium sulfate that has been produced. So what I'm going to do is I'm going to start to gently heat the solution over a Bunsen burner. So what I've got is I've got an evaporating dish, I've got a beaker with some water in it to act as a water bath, and then I've got, you know, Bunsen burner, tripod and a gauze, and I've got my solution here. So I'm just going to add a little bit into my evaporating basin. I'm not going to add loads, otherwise it'll take a very long time to crystallise, and we only want to have a look at a little bit of this. Now, it's not evaporation. I'm not evaporating all of the water from this. I want to do the process of crystallization. So I'm only going to heat this until the first crystals start to appear, which would show me that I've got a saturated solution. So there is as much of my ammonium sulfate dissolved in the liquid, in the water at that point, as possible. And then I'm going to remove it and I'm going to leave it to crystallise over a few days. And that's going to give me much bigger crystals than if I just evaporated it straight away, which is why I'm also using the water bath. I want to heat it a little bit more gently than just putting it straight on top of the Bunsen burner. So I'm going to get the Bunsen burner lit now. So I'm just going to leave this for a while to start to evaporate, and when the first crystals start to appear, I'm going to remove it from the heat and leave it to crystallise. So it might be quite hard to see this on the camera, but I have stopped the Bunsen burner. I've turned it off because there are some very small crystals starting to form around the edge of the solution. They're very, very tiny, very, very faint, but they are there. So I'm going to leave this to cool for a bit, and then I'm going to put it to one side and come back in a few days to see the crystals that have formed. So now, after a few days, you can see that the ammonium sulfate crystals have formed in the evaporating dish. So you can kind of see 2 rings of crystals. So you've got a ring around the edge with smaller crystals. They almost look like sugar grains or salt grains. And then you've got these larger, longer crystals that are formed in the middle. So the smaller crystals around the outside were formed during the evaporation process, but these larger crystals formed in the middle
over a few days through the crystallization process as they came out of solution. Now let's take a look at some exam questions related to making fertilisers in the lab. Now let's take a look at a range of exam questions on fertilisers. Typically, questions on this unit and using resources in general will rely on a lot of knowledge application. Often questions will contain a lot of information that you'll need to interpret and use alongside your own knowledge. Questions will also often involve evaluation or giving opinions, and questions about fertilisers are usually closely linked to the Haber process, but we aren't really going to focus on those today. So let's take a look at these questions. The first one is nice and simple. So, fertilisers are used to improve agricultural productivity. Ammonium nitrate is used in fertilisers. You name the two compounds used to manufacture ammonium nitrate. So you can work this one out easily from the name linked to the chemical changes unit 2. So you should have learned about naming salts there, because ammonium nitrate is just a salt produced in a neutralisation reaction. So remember, in these kinds of reactions, ammonia acts as an alkali. So the two compounds used for this reaction are ammonia and nitric acid, which always produces our nitrate salts. So looking at the second question now. A fertiliser contains the following information on the label. So it says NPK value 14, 11, 11. Explain why this information is useful to farmers. Now, you don't need to know much about specific NPK fertilisers, but you do need to know what this ratio means. It means that this fertiliser is 14 parts nitrogen, 11 parts phosphorus, and 11 parts potassium. So this is really useful for farmers, because what that's doing is giving the different percentages of nitrogen, phosphorus and potassium. That's what the NPK stands for, it's those symbols, and that's what those numbers are representing, but they're given as parts rather than percentages. But either way, it shows them the same thing. And with this information, it allows farmers to choose the mixture that is right for them, because different soils and different plants are going to require a different mixture. Let's take a look at the next question. So this one follows on from the other two that we've just looked at as part C. The figure below shows worldwide ammonia production and world population from 1950 to 2010, and then we've got a graph here, so you can see the population in billions on this side, the production of ammonia in millions of tonnes on this side, and then the years going along the bottom. Use the figure above and your knowledge to explain the relationship between ammonia production and world population. So we need to be using the graph to answer this one. So this is a 3-mark question, and although our command word is explain, we need to make sure we're also describing the link that we're seeing on the graph. If you ever see explain in a question, you should imagine it's really saying describe and explain, because that's what the question really wants. And that goes for any question across the sciences. So let's start by describing the graph, and you can see that there is this clear positive correlation between the population and also the ammonia production. So we would describe that as world population increases, ammonia production increases. So that's how we would always describe something like that. It's always going to be our first line when we are talking about a graph. So let's look at the explain part. Why is this the case? Now, I think actually this is quite a challenging question to get all of the marks. It looks really simple at first, but I feel like you need to dig a little deeper into what it really wants. So first of all, let's consider what ammonia is actually used for that could be linked to population growth, and think about the topic that we're doing. This is, of course, fertilisers. So ammonia is used to produce fertilisers. Now, how would they help with population growth? Well, without fertilisers, there would be no way for humans to produce enough food to sustain the population. So, more fertilisers are needed to make enough food for the growing population. So that would give us all 3 marks for this question. So moving on to question number 2. This is just a 2-mark question here. So I'm going to read this to you. There's a lot of information on this page. About 4/5 of ammonia production is used to produce fertilisers. One of them is known as NPK. It is made in the following way. Some ammonia is converted to nitric acid, which is then mixed with phosphoric acid. The mixture is neutralised with more ammonia and the solution is partly evaporated. Potassium chloride is added to form granules. The granules are coated to make the fertiliser free-flowing. Complete the flowchart for the production of NPK by writing in the names of the correct chemicals in the 6 boxes. And you can see the 6 boxes as part of this diagram. So at first glance, this question is a lot, okay? You might be thinking, I've never learned the full industrial process for making fertilisers. And that's fine, because you aren't expected to. You're expected to be able to use the information in the question to answer this one. You don't really need to know a lot to answer this one. It's all in there for you. It's a lot for 2 marks, but I think this is a really interesting kind of puzzle to try and figure out. So we're going to take it line by line to fill each section in. So let's go to this first one then. So some ammonia is converted to nitric acid. So, okay, where's our converter? Well, our converter is here. So it must be above that we have ammonia coming in. And then it says that it is being converted to nitric acid. So we must have nitric acid coming out. Okay. And then let's see if we can find what this is mixed with. So some ammonia is converted to nitric acid, which is then mixed with phosphoric acid. So that must be the next box. That's what it's being mixed with, because you can see here that you've got these arrows linking them together. So it must be phosphoric acid, and they are passing into the neutralizer, which has this empty box up here. So let's take a look at the next line and see if this can answer this one. So the mixture is neutralized with more ammonia. Okay, so our neutralizer, so going into the neutralizer must be some more ammonia. That's what it is telling us. If we've got neutralisation, that tells us that we are making this ammonium salt, but also water, because neutralisation reactions give us salt and water. So let's have a look at what the next part is. So it's neutralised with more ammonia and the solution is partly evaporated. Well, this is our evaporator that we've got here. Out of that mixture of a salt and water, what's going to evaporate? Well, of course, it's going to be the water. So water would come in above that box. So you can see already we've got 5 of the 6 completed, and let's look at our last few lines. So potassium chloride is added to form granules. Well, I guess that this is what is happening in the granulator. So of course it's potassium chloride that is going in here. And we filled all of our 6 boxes, but let's take a little look at this final sentence. The granules are coated to make the fertiliser free-flowing. And you can see that down here you've got the coater that coats those granules, and then that's the fertiliser that they sell. Nothing else to add at that point, it's just a little bit of additional information. So that's quite a lot of work for 2 marks, but you didn't need to know anything in other than, I suppose, that water is produced as a product of that neutralisation reaction. Everything else you should have been able to work out from the information that is given to you up here. Now let's look at question 3. The flow diagram shows some stages in the manufacture of ammonium nitrate, which is NH4NO3. And you can see that they've put a diagram into this question as well. So if there is a diagram, it's there to be used. Older questions that pop up may have pictures that aren't that useful, but something like this definitely is. So always pay attention to diagrams, annotate it, label it, draw on it, whatever, but just don't ignore it. So this one we can see is mostly a diagram of the Haber process, so that's this part here, with this additional bit on the end with the reactor to make ammonium nitrate as a fertiliser. But this you should recognise as being from the Haber process. You know, the typical high temperature, high pressure ion catalyst is a big clue, as well as your link with the unreacted gases being recycled through the converter again. So let's take a look at our first question then. Which elements are obtained from the raw materials that make ammonia in the converter? So it's asking us about ammonia, and there is a bit of a clue here in that methane and air are being fed in to the converter at the start. So if we link this back to the Haber process, we should know that methane is the source of hydrogen and air is the source of the nitrogen that goes into our ammonia. So, of course, 2 parts of ammonia, nitrogen and hydrogen. You would also know that from the formula, which is NH3, but that's just a little bit of extra information from the diagram that could help you. So let's take a look at part B. Suggest the purpose of the ion catalyst. It's the same reason that a catalyst is used in any reaction. It helps to speed up the reaction. It increases the rate of reaction. It gives us that alternative reaction route with a lower activation energy. But more simply, we just need to be able to say it speeds up the reaction. So question C, farmers add ammonium nitrate to the soil. Explain why. These questions always tend to be of a very similar vein. So these salts are of course used as a fertiliser, which is to help plant growth. So they almost always want you to be referring back to the plant growth with these kinds of questions. But that's nice and easy, 2 marks, because these ammonium salts are always fertilisers. Fertilisers help plant growth. Okay, this is the final question that we are going to look at today. So nitrates such as ammonium nitrate are added to the soil to help plant growth. When rain falls, nitrates dissolve and can end up in drinking water. Nitrates in drinking water can stop respiration in babies. This only happens if there is a lot of nitrate in the drinking water. Plants use nitrates for growth. Humans need plants. Should large amounts of nitrates be added to soil? Give 2 reasons for your answer. So here's one of those older questions with a sort of useless picture. You can just see it represents a sack of fertiliser, but I've just left it in anyway. So with this type of question, they don't care whether you say yes or no, so long as it's justified. They also give you some information in the question that you can use to help make those judgments as well as your own knowledge. So let's look at yes as an option first and see what we would write in that situation. So let's take a look in the question and see what evidence we have for yes. And it says up here, help plant growth. So we can use that as our first reason. And why does that help us? Well, it means more food can be grown, which gives us our second reason. So now let's look at the options linked to no. So for this one, we're going to need to use some evidence that's given to us in the question. So we can see up here, it clearly says that it can stop respiration in babies, which would lead to death or serious harm. So that one's a definite reason against, okay? So it could kill or harm babies would be our first reason. Now this happens only if there are lots of nitrate in the water. And this question specifically asks about adding large amounts of fertiliser. So another reason against large amounts of fertiliser could be that we could use small amounts instead. It's not going to be quite as effective, but it would still help. I feel that the reasons for yes on this one might be a little bit more than both reasons for no, but it would be up to you which you would choose. You don't get a mark for just yes or no, so you have to make sure that you're including your reasons. And it's always the same with a question like this. Make sure you're backing up everything you're saying with some evidence. So that's it for this video. I hope that it was helpful and that you've learned more about the process of making fertilisers. So thank you very much and goodbye.